Hello, dearest participants. I welcome you to this very exceptional class again, which is our second class on state space equations in modern control engineering. You will recall that in our last class, we made an introduction of the state space equation. We showed you how to develop the state space equation given a differential equation or either second order, third order, fourth order, or whichever order you are given. We also generated from the developed state space equation. We showed you how to find out the the system matrix, the input matrix, the output matrix, and the direct axis matrix. In this class, we are going to further our study on state space equation by seeing how we can do some analysis using the state space equation. Let's get into the class proper. Here we are going to start first with how to develop the transfer function from a state variable model representation of a system, which is of course the state space equation. Recall, we have the input equation and we have the output equation. So how can we develop the transfer function from this state variable model? One important question worth asking is, why do we need the transfer function? Of course, the transfer function is also important in our analysis of the system. We are going to see subsequently in this study that with the transfer function, we'll be able to develop what is called the characteristics equation. And through that characteristics equation, we can determine the eigenvalues of the system. And having found the eigenvalues of the system, that will probably give you further insight into the system in terms of its stability. But we're not going to consider that in this class. Perhaps in our subsequent class we are going to look at that. For this main class, we are going to be focusing on how to develop the transfer function having been given the state variable model. So let's move into it. It's a very simple step to take. First, he said it may be reasonably asked at this point how the state variable description, which is in time domain, relates to the transfer function representation. Consider a state variable model initially at rest. I hope you understand this language, initially at rest. Okay, let's move. Where x is the state vector, u is the input, and y is the output, the Laplace transforms of the equations are given by. Yes, to carry out this solution, so we just go straight and Laplace transform this equation. And when we Laplace transform this state variable equation, we will have, first, remember that this is a first order differential term. So when you Laplace transform this first order differential term, you have s of x minus s of naught, which is equal to e s of x plus b u of x. That is in Laplace transform. And also the output equation, and you have y of x is equal to c s of x plus d u of x. Now remember that this is, what does this represent? This represents simply an initial condition s of naught. But remember, for the transfer function that we tried to compare initially when this class was introduced, we tried to compare the transfer function and the state variable model representation of a control system, and we said that for the transfer function, it does not consider any initial state of the condition or any initial state of the system. Rather, it continues with the present state of the system. So it doesn't have anything to do with the previous knowledge of the system or how was the system before now. So it considers that that system was totally at rest. So that's the reason for this language, at rest. It considers that the system was initially at rest, that doesn't give you any previous knowledge of the system. And I think that was part of our comparison between the classical control system and the modern control system. So now we are going to assume that this S of naught is 0 because the system was initially at rest. So if it was initially at rest, all initial conditions will be considered to be 0. So when we consider that to be 0, this equation will reduce to this. So you see that, and this will give you A of that plus B of this, just like we have here. The only thing eliminated is this S of naught, and then you repeat this side. Now let's continue. Now at the end of the day, this is the equation. What do we do here? Let's look at it again. We collected like terms by moving this term to this part of the equation, and let's look at that. So we see when we move that, it became negative. So, and we had this equality sign, and this is where to represent this, but we want to also continue with the analysis of this. When you move it, it becomes, we have told you initially, this is a matrix. This is a matrix. So in subtracting x from this matrix, you must introduce an identity matrix, and that's why here at this point we have x of I minus the matrix, which is what? A. And what is common to both of them? We know S of x is common, and that will give us Bu of x, like we have. Remember, this Bu of x is just as we have it here, this Bu of s. When you move this to this point, you should be equating to Bu of x. Now we have that this way. Now, so remember, we can make S of x the subject. When you make S of x the subject, what are you going to have? You're going to have S of x is equal to xi minus a, just this, dividing Bu of x. Mind you that this minus 1 here implies that it is dividing this component. So when it divides this component, this is what you are going to have. So we can either write Bu of x all over xi minus a, or Bu of x times xi minus a raised to the power minus 1. I hope you understand this mathematical representation. Then we go substituting in the output equation we get. That is, we have already established a relationship for S of x. We've established a relationship for S of x. Then now we substitute what we have here, because remember, in the equation for y, look at that, in the equation for y we have C S of x. So we're going to substitute that S of x into this so that we can, so let's look at that. So I have y of x is equal to C. Now this is the value for that S of x, which is this. We substitute that into the equation now, plus du of x. Remember, let's look at it. This is the du of x like we have. So let's continue. So remember that the transfer function is actually the ratio of the output of the system divided by, the ratio of the output of the system to the input of the system. That's going to give you the transfer function gx. Recall, that's the representation of transfer function. So now we have developed an expression for the output. This is an expression for the system output y of x. That's that. So now this is also for what? U of x. So of course we can say g of x is equal to y of x all over u of x, and that's going to be what we have here. So we say g of x is equal to, now this whole expression divided by what? U of x. Of course, when we divide that by u of x, you see, when you divide, it's like dividing this by u of x. You see, this will go, that will go. So at the end of the day, you'll be left with cs of I minus a raised to the power minus 1 b plus d, and that's what you have here, b plus d, while the u of x is gone. So you see, at the end of the day, this is now our transfer function. Wow, this is beautiful. So we have been able to develop the transfer function and equation for the transfer function using the state variable equation. So let's look at the components of the transfer function. So we see that the components here includes c plus ci minus what? Minus, includes, the transfer function includes g of x, which is equal to c into x of I minus a raised to power minus 1b plus d. So you know that this is a matrix. Yes, this is a matrix, the direct axis matrix. So this is also a matrix. So you can see that this is also a matrix. So this is the input matrix. You know that this C here is the output matrix, and you know that this A here is a system matrix. So let's consider an example where we can apply this, and we'll look at and see how it looks like. We have told you that one of the importance of the transfer function is that from the transfer function we'll be able to develop what is called the characteristics equation. And when you have the characteristics equation of the system, you'll be able to determine the stability of the system using the characteristics equation, because from the characteristics equation you can calculate the eigenvalues of the system, and from your eigenvalues you can determine if your system is stable or not, or study what kind of stability that we have in that system. So let's look at an example. We have the state equations of a system are given by this, that. So we are asked now to what? Determine the transfer function for this system. Already we know that looking at this state state equation, we can see that this is what? This is our matrix A. This is what? B. We can see this is U. Then because we don't have the D, we can assume that D is 0. So of course we've been able to develop this, that, and we have seen that. So but let's look at it and see clearly. So we know already, like we have proven, that the transfer function equation is equals to g of x, which is equals to c s of I minus a raised to power minus 1b plus d. Good. Having done that, let us work out this. So you can see first we calculate s of I minus a raised to power minus 1. We are trying to work out for this expression. What is this expression? So you see that expression represents s of I minus a. We already know what a is. Now this I, like we told you, is an identity matrix. So you can see x into the identity matrix 1 1 1 0 and 0 1. Then minus, what do you have? That you have, this is what? The system matrix, minus 2 0 minus 3 and minus 1. So at the end of the day, this is going to be equal to, when you have 1 minus 2, it's not just 1. You mind you that you're going to be having this x times 1. So this place now is what? X. So x minus 2 will give you x plus 2, and this will be x times 0. So 0 minus 0 will give you 0. In the same case, you have x times 0. So you see that 0 minus 3, what would that be? The plus 3. And here we're going to have x times 1, and you have x here minus 1, that will give you x plus 1. So at the end of the day, mind you that this is telling you that this is the inverse of this whole system here, the inverse of this matrix. So now, to get the inverse of the matrix, please do not forget that the inverse of the matrix, what does that mean? The inverse of the matrix is simply, like we have here, the adjoint of the matrix all over what? The determinants of the matrix. That is actually how to determine the inverse of a matrix, because this thing represents the inverse here multiplied by b. So we have at the end of the day. So we need to get the determinants of this matrix. So what is the determinants of this the determinants of this matrix? Of course, you know how to determine the determinants of a 2 by 2 matrix. You're going to be having this times that minus this times this. So at the end of the day, look at that. So you know this times this will give you 0. So you are going to be left with just these two components, and that's what we have here. So when you do that, you expand it, you're going to be having x squared plus 3x plus 2. Good. So now, say then, letting the determinants be equal to this for convenience. So you know, of course, we are just doing this for convenience, but normally that this means actually the determinant. So to make our work look a little beautiful and not complex, already we have determined the determinants, so we just go straight and do this. You know, of course, we do this. We have told you that the inverse of this matrix means the adjoint of the matrix, right, all over what? The determinants of the matrix. So now, how do we get the adjoint of this matrix? So look at that. So how do we get the adjoint? So to actually get the adjoint of this matrix, you know definitely well that what you can do here for a 2 by 2, you can go and study for a 3 by 3 system, for 3 by 3 matrix, but for a 2 by 2 matrix, we just simply, we can get its adjoint by what? What do you do this? You transpose. You understand? That is, you move this to this point and move this to this point and negate the off diagonals. So what do you mean? You interchange the diagonals and negate the off diagonals. So let's look at what we mean here. So what we mean is that you interchange that. So you can see that when you interchange, you move this to this and move this to this point. Then you negate by adding negative here and negative. Multiply this side by negative and this side by negative. So at the end of the day, what do? You interchange. So when you interchange, you can see that these have crossed, and you have 0 here, you have 0 here. Remember, we said divided by what? The determinant. So this is the determinant of that matrix. So can you see that? So when we have the determinants of that matrix, so we have S of that divided by what? The determinant. We have already assumed for convenience sake, instead of putting all of this on divided by this and this divided, for convenience, we are leaving it in this shape. So we have change in x, and you can see that. So all the whole components of the matrix divided by what? The determinant. So when we do this, remember that this time here is 0. So remember that we have already said you negate, so this is minus 3 all over what? The determinants. And now you have the inverse of this matrix. So having developed the inverse of the matrix, let's go to the next. So this becomes, it said, and the transfer function is now given by this. So we see that, remember that this, what is here? This is C and this side is B. Let's look at it again. So you can see we now bring in the component C and what? B. Remember that D is 0, so we are no longer bothered with D. The components we're working with is B and C. So now look at that. So you can see this is a matrix C and this is a matrix B. So of course, whichever one you choose to multiply before the other, there's none you use that is wrong. You just go through the rules of multiplication. So of course, if we decide to start from this, like we have here, we have that this will multiply this plus this times this. You know, this multiplied by this plus this multiplied by that. So when we have this multiplied by that, it will be 0. This multiplied by this, it will bring back this. So we now have this expression. So we go down. The next one becomes this times 1 plus this times 2. So when we have this times 1, what are you going to have? You're going to be returning minus 3 all over what? Determinants. Then this is also going to be this times this, you have 2x plus 4. divided by this. So when you have minus 3 divided by this plus 2x plus 4 divided by this. Now when you say plus, note plus 2x, you have plus 4. Now mind you that these two now will now be adding, so it will now be minus 3 plus 4. And what is minus 3 plus 4? You're going to be having 1. So at the end of the day, we'll have 2x plus 1 divided by the determinant. So, and you can see 2x plus 1 divided by the determinant. Just remember, we still have the matrix C still here. So what do we do next? We still go by the same multiplication. This times this plus this times this. So that is 3 times this will give you 3x plus 3 plus 1 times this, which will be 2x plus 1. So here you're going to have 3x plus 3 plus 2x plus 1, all divided by this determinant because their denominators are the same. So when you have 3x, so this 3x plus 3 plus 2x plus what? Plus 1. So at the end of the day, you're going to have this 3x plus this 2x, which will give you 5x. Then here you're going to have 3 plus what? This 1, and that will give you what? 4. And that's what we have here, divided by what? The determinants. So remember that we calculated that our determinants, we avoided to be repeating it. So at this point, we'll bring it back to be x squared plus 3x plus 2. This is the determinant, is actually the value of this determinant s. Please let's reconfirm that we are correct. So already we told you that the determinant, which is this, the determinant of this, which is that, we have told you that is this. So you can see where we repeated it. So now this is what? Our transfer function. Of course, from this transfer function, like I told you, one of the applications here is that we can, when we equate this denominator here to 0, we can get what we call the characteristics what? Equation. And from that characteristics equation, we can determine the eigenvalues of the system, and from the eigenvalues of the system, we can comment on the stability of the system. I hope this is quite straightforward. Now, solution of state equations. So we are through with looking at the transfer function, and I believe from the short example we've given to you, if you have any form of equation given to you, you can actually develop the transfer function for that system. So here we're going to look at the solution of state equations. We have only shown you the state variable equations, but we have not been able to develop a solution to the state variable equation. The solution, of course, will be in terms of looking for the value of what? This solving for actually what? S of x. I mean solving for x of t alone, s of t. So here it said one way to solve the state equation is the use of Laplace transform. Yes, of course, there are several techniques or approach used in solving the state equation, but one of the approach, which is what we're going to be considering in this study, is the use of the Laplace transform. You see, the Laplace transform will play a very vital role here. You know, the Laplace transform, like we know, one of its very beautiful application is the simplicity it gives to us in solving differential equation. And you know that this state equation is actually, starts with what? A differential equation. That is the input equation is a differential equation. So we take the Laplace transform. Remember the same thing we did for the transfer function when we did the Laplace transform. So you can see the Laplace transform. I hope you have not forgotten that when you Laplace transform a first order differential term, you're going to have this. So is equal to that. This is s of t, bu of t. You find their Laplace transform, and this is what you're going to have. So Here we wish to solve this equation for s of x like we initially informed you. To do this, we rearrange the last equation. Of course, what we're going to do is to make s of x the subject. So mind you, for transfer function, this was assumed to be 0, but in this case we are not making that assumption. We are leaving everything as it is because we are trying to solve for the state in the state space mode. Of course, where we know we consider the initial conditions of the system. So you can see, so here we're not eliminating the initial condition. So we have s of I, and you can see that when you cross multiply this to this point and this goes to this point, so this becomes negative, this becomes positive, and that's how you have this expression here. When you do that, remember that we can afford to say s of x divided by s of x, make it the subject, move this to divide these two components. So like we have before, when we say s of x is equal to, so when it's dividing, you see we can introduce this minus 1. Is that clear? Now that, because this actually means s of naught divided by this plus bu of x divided by this. So when we do that division, remember that this is going to be, we can still represent it, instead of putting the division, we can just say multiply s of naught by this raised to power minus 1, and bu of x will multiply it by what? This component raised to power minus 1. Okay, so we have developed an expression for s of x. So let's go. Wow. So what do? We do carry out the inverse Laplace transform, of course, because mind you, we want to solve and bring it in the time domain. What we did was to move it to the frequency domain, then convert finally again to the time domain. So when we bring back to the time domain, this is s of t is equal to this plus that. Wow, one will be confused and wonder, why do we have this integral here? Of course, if you've done your Laplace transform very well, you'll be able to see what is happening here. This is actually convolution. What has taken place here is actually convolution. Mind you that this is t minus tau bu of what? Tau d tau. So why do we have this component? Now let us start with this component. Let's look at it again. So you can see that this component, this is s of I minus a. Now for this component to determine it, mind you that this is to find the Laplace transform of xi minus a. To determine its Laplace transform is equivalent to saying exponential e of t. Now s of o, mind you that we have that, which is this s of o exponential e raised to power what? E of t s of o plus. Now when you look at this term also, you see that this term, this is a combination of two terms, two frequency terms. That is, this is a frequency term si minus a inverse of minus 1. This is a frequency term, and this also is a frequency term. So mind you, this is like multiplying two Laplace transforms. So when you look at the convolution integral, you see the convolution integral is actually used, when you multiply two Laplace transform, you can convert it to what? The time domain, by taking what? The convolution of those two transforms. So go and look at your convolution. So when you do that, you should have this. So you can see that it is simply just this, delayed. Instead of putting t, you have now delayed by what? Tau. Can you see that? In place of this, you now have this delayed by tau bu. Now instead of t here, you're having what? Tau, and you are integrating with respect to what? The tau. So you can see that where your limit is from 0 to t. So the only difference here, you can see that it is just this component delayed by tau bu of tau. So please go and look at your convolution integral, and you'll be able to see what has happened here. So this is Now the solution actually now in time domain. Can you see that this is a solution in time domain? So all that we're doing, we are coming down to this. Is that clear? So here the exponential matrix E of A of t is called the state transition matrix phi of t and is defined as. So we say that this term here is called what? The transition, the state transition matrix. So please take note of this term because you may be required to calculate the transition matrix. So what is the transition matrix? It's just this component exponential A of t, where A is the system what? Matrix. So look at that. So look at the way it represents. So you can see that in terms of in the frequency component, it is what? The Laplace inverse. This means Laplace inverse of xi minus e raised to power minus 1. That is the component that gave us this. I hope you still recall the component. Let's look at it again. So you can see, mind you, that here we have to take the inverse Laplace transform. The inverse Laplace transform of this component. So the inverse Laplace transform of this component gave us what we call the transition matrix. So you can see that. So it then means if you are asked to calculate the transition matrix, you can simply go straight and what? Do the inverse Laplace transform of xi minus a, where a is what? The system matrix. So this can be simplified to this, to this form, where this of x implies this in frequency domain, this is it in time domain, this is it in frequency domain. That is this term here where we have Laplace inverse Laplace transform of what? A frequency domain component. So that's that. So we have that the exponential matrix E A of t represents the following power series of the matrix A of t, and so we see that this component can be reduced to this form. Can you see that? Okay, which of course at the end of the day we can say s of t, which is that s of t. So instead of saying putting all of this, so we just put phi of t s of o, because phi of t is equal to this entire component, which is equal to this. So you can see phi of t and x of naught, yes, the initial condition, plus that, you see that, which is this integral. So we have that this place, we told you they are the same. The only difference is the signal has been delayed by what? Tau, b u of tau, the tau. So we have solutions in terms of st of o. Now what we're trying to say is, what if we have, this is equivalent to saying phi of t minus 0. So what if we have that this, we are trying to determine the solution for a delay of time to. So of course we can get a solution in terms of that. The solution will be of this nature. This, you see to, then we'll have this, for that delay, plus this. Now in this class we will not be considering problems involving this. So we'll just be considering just this particular term. This is what we will be considering. So let's just do a simple recap of what we've done so far. So what we have tried to do is to develop a solution for the state equation in time domain. We started first by Laplace transforming the state variable equation. After doing the Laplace transform, putting it together, then making s of x the subject. Then at the end of the day, we did the inverse Laplace transform to bring back the function to the time domain. And when we brought back the function to the time domain, So this is what we have. And remember that we said that this component is actually called what? The transition matrix. And this transition matrix can be gotten by what? The inverse Laplace transform of what? This frequency component. Yes, the inverse Laplace transform of this frequency component will give you the transition matrix. And we have told you also that this is the this component in what? In frequency domain. That component in frequency domain, this is what is going to give to you. And from there, this may not be too necessary. If you are asked to solve this may not be too necessary. You are supposed to just stop here. If for instance we told you to use the state variable equation and prove the general solution, this we can regard this as also the general solution for what? The state variable system. So when you have the state variable equation, this is a general solution for it. So we can tell you to get to this general solution. So you may not be needed to do this, but you can indicate that this component is a transition matrix. So please do not forget, but this is not too necessary. If you want, you can reduce it to this, because this is a further simplification of this expression to this term. And this also may not be necessary except you are asked. Okay, let us take this footnote here. We have that the system response S of t is equal to 0 input response plus 0 state response, which is equal to what? System complete what? Response. What is this really trying to tell you? So you can see this is a 0 input response. Now what do we mean by the 0 input response? The response of the system when based on all the initial conditions, because mind you that the beauty of this modern control system is still, do not forget that we said is it considers the system's initial condition. So you see, so the total response of the system, which is the total signal system response, will be response as a result of what? The internal conditions of the system, which is this, based on the initial conditions, and the response based on what? The input. So this is the input axis, that is from 0 to t. So it integrates the response from 0 to t. I hope you get to understand this. This is the basics of system response, and I think you should arm yourself with that knowledge. Wow. So properties of the state transition matrix. So these are a few properties. Well, you can just look at it for your own. That we have that when you have E of A, if that t is 0, that is what we have here, that t is 0, this will be equivalent to what? So you can go and verify that and do that test and be sure that these things are correct. So give them a try. These properties, you can do a test of these properties to be sure that these properties they are correct. So look at this also. We have said that this is equal to that. You can see. So you can go and verify all of this to be sure they are correct. So this is where we stop for the properties of the transition matrix. Let us now consider an example to help drive home all that we have learned. So we have here said obtain the transition matrix of the system, given the system matrix as what? E is 0, 1, 0, minus 2. Of course, we have told you we start by calculating the matrix A. Let's look at how the transition matrix can be obtained. So you see that the transition matrix phi of t is given as what? The inverse Laplace transform of this matrix, of the inverse of this matrix. So we start first by looking for what? This matrix, gets its inverse, then of course get the Laplace inverse. So let's get back to it. So of course, so this is the matrix, that is it. To get this matrix xi minus a, we have what? This s multiplying the identity matrix, which will be x0 0 x minus this is 0 1 0 and minus 2. So that will be equal to this. So you can see that when we say x minus 0 will be x, of course, 0 minus 1 minus 1, 0 minus 0, 0, 0 minus minus 2 will give you s plus 2. So you see, that is that. So now to get determinant of this, because remember we told you that the inverse, this inverse, which is what we are going to look for, the inverse of this matrix is actually what? The adjoint of the matrix all over its determinant. So the determinant of this matrix will give us this, which is this times this minus this times this, and that is what we have here. So what is the adjoint of that matrix? Of course, what is the adjoint of that matrix? The adjoint of this particular matrix, which is that we are going to get the adjoint by, we told you, is actually what? How do you get the adjoint by what? For a 2 by 2 matrix, you just interchange the diagonal elements and negate the off diagonal elements. So when you interchange the diagonal elements, you have this will go here, and this will come down to this side, then you negate here, this plus this minus 1 will become plus 1, and this will be 0. And of course, that is what we have here. So like we told you, that the inverse, which is what we are driving at, so the inverse of that matrix will be what? The adjoint of the matrix all over the determinant of the matrix. So we have gotten, this is our determinant, this is the adjoint, that is to say this whole matrix divided by this. So that is, this will be divided by this, this will be divided by this, this will be divided by this, this will be divided by this. So if we divide this by this, if we divide this by this, we'll have that this will cancel this, so you will have at the end of the day 1 over x. Now if you do the same here, this will be 0, of course is divided nothing. You do here, this is 1 all over x plus this, and that's why you have this. So this is x all over this x will cancel x, and that's why you have 1 all over x plus 2. So you can see that. So of course, so what do? We know that our transition matrix is actually what? The inverse Laplace transform of what? This matrix. So what is now the inverse Laplace transform of this entire matrix? So this is the matrix, we substitute, we get the inverse Laplace transform. So you take the inverse Laplace transform of this is converting this to time domain. Of course, you know that this will become 1, and you know what you have to do here. What are you going to do here? This, of course, these two components will lead us to partial fraction. So we do the partial fraction of these components, such as we have a all over x plus what? B all over this. Then you find the component for a, find the component for b, then of course do the inverse. Then for this is direct. Of course, this is going to give us exponential minus 2t, when we take the inverse Laplace transform, and this of course becomes our transition matrix. I hope you're not feeling troubled. Of course, Laplace transform is the basics for this study. So you just need to look at just simple Laplace transforms, to help your understanding of this topic. So let us look at further example. Now we have another system. We have a system is defined by the state equation. Now this is the state equation. Now in the former problem we did for you, we were able to give you A, that is a system matrix. In this, you have to get your A from the system you have been given. So of course, you said you were given this system and we are asked to what? Determine the state transition matrix phi of t. Find the zero state response if a unit step is applied. So you can see this is what we have here. Then we can now move with what? The solution. Now we said to find the state transition matrix, we first calculate the matrix. Remember, that was what we did for those cases. We first calculated for this matrix. So when you calculate for this matrix, this is what you're going to have. Of course, xi minus a. So of course this is in the same, this is, remember that in the other case we just went straight and did xx. So this is supposed to be x0 and this is 0x. So when you do that, you have that x minus 3, that will give you x plus 3. Mind you that because this will be minus minus, yes, and we have 0 minus 1. For this case, 0 minus 1 will give you minus 1. Here you have 0 minus 2, which is minus minus 2, which will give you plus 2. Then you have x here. Then this is x minus what? 0. And of course, you're going to have what? You're going to have x. So now let's move to this side. So we said the determinant of the matrix X. Now, of course, you know, like we said, the inverse of this matrix, which is what we're driving at, is actually the adjoint of the matrix all over its determinant. So we'll look at it. So the determinant of this matrix, of course, you know, to be this times this minus this times that. And that's what you have here. If you expand, you're going to have this, so you can factor out to have this. So we have adjoint of the matrix. What is the adjoint? Remember, like we said, that's what you interchange the diagonal elements and negate the off diagonal elements. So when you interchange, you have x will go here, x plus 3 will come here. Then this place you're going to have minus 1 will change to what? Plus 1, and this is plus 2 will change to minus 2, and that is what you have here. So finally we substitute, like we said, the inverse is going to be the adjoint all over the determinant. So this is the determinant and this is the adjoint, and this is our adjoint here. So divide by what? This determinant. So we are going to have x plus 1 plus x plus 2 dividing by what? Divided by this component here. So when you have that, you're going to have this adjoint divided by what? The determinant. So this is the adjoint, s all over the determinant, which is that. Good. 1 all over the determinant, that is that. Minus 2 all over determinant, that is this. S plus 3 all over what? The determinant, and this is what you have. So having done this, our next line is to what? Let's look at it. Good. Next plan is to look for the inverse Laplace transform and bring it to time domain, but we can't go straight because these are partial fraction terms. So of course we must work on this partial fraction to split them so that we can get the inverse. So of course you still remember your partial fraction, and what you can do, that this will become e all over s plus 1, then plus, you know, b all over s plus 2. You know, this is also e all over s plus 1 plus b all over s plus 2. In this case the same thing, in this case the same thing. So using that, find the components a, b. So you can see we have found ours and we have gotten them, we have splitted them, so you can see the way they are here. Then we are now ready for what? The inverse Laplace transform. So we take their inverse. So when you take the inverse of this, you have this. You take the inverse of this, you have that. You take the inverse of this, you have this. 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 Take the inverse of this, you have that. So wow. So you can see that we already have some solutions made available for us. So you can see now we've been able to get the transition matrix as required. Wow, very beautiful. I think it's straightforward. Then the next question says, if a unit step is applied as an input, the unit step, that is 1, of course, applied as an input, then we have that u of s, because the unit step is 1 in time domain, but in frequency domain it is actually what? 1 over s. So we have it converted in frequency domain to 1 over s. So we said the zero state response is, we have to look for what? The zero state response. Now do not forget that we told you that the total response of the system, like we calculated, is equivalent to what? The zero input response plus the zero state response. So which is the zero state response? Let's refer back to where we are coming from. So you can see, look at it here. This is the zero input response, which is response due to the initial conditions alone. This is the zero state response, which is response due to the input alone. You can see that's the input alone there. So in terms of the frequency domain, you can see this is it. So you can see this is this. This is just this multiplied by that, and you can see in terms of, so our interest here would be to look also for this, identify this, because we have already calculated it here. So we just identify that, then multiply it by what? B, and multiply also by u of s. Then look for the what? The inverse, because you know this is frequency domain. We can look for the inverse in time look for the inverse of this transform, convert it to time domain, and then we already have the zero state response. Okay, so this is where we are. So of course we already told you we have this, so we just go straight and bring it in. This is what we have here. So what do we now do? We multiply this factor by what the matrix B. So what is matrix B? Our input matrix. Do we have our input matrix? Of course we have our input matrix to be what? 0 and 1. So of course we put that. So you see our inputs 0 1. Then we already know that our input is a unit step input, and in frequency domain is 1 over s. So you can see that. So this, of course, you know, this means 1 over s times 0, which is 0, 1 over s times this, which is 1 over x. So of course we can now expand. Now we expand by multiplying this times this plus this times this. Mind you, when we say this times this, so this times this becomes 0, this times this, remember that this will be also multiplying this. So when we multiply everything here, you're going to be having 1 over x at the end of the day times this factor. So and that's why you have this while this remains 0. So we do the same thing here. We'll come down here, we say this times this, which is of course 0, plus this times this, which of course will be multiplying this also. So you have, when you multiply everything here, you'll be having s plus 3 all over this, because this will multiply this, and mind you that this will multiply this also, and you have this at the end of the day. Of course we have this now to convert this to time domain, because this is now in frequency domain. To convert to time domain, remember that what you're supposed to do is to do the partial fraction so that you can split this component. So we do the partial fraction, and this is what the partial fraction will give to us. And having obtained this partial fraction, you know, from this point you can go straight and look for what? The inverse Laplace transform. So if you take the inverse Laplace transform of this partial fraction, you are going to arrive at this. Wow, this is nice. So then we have a problem here for us to try our hand on. It's important you realize that what is fundamental in really solving some of these problems is your understanding of the Laplace transform and partial fraction. Of course, for you to solve the Laplace transform, you must have a good understanding of your partial fractions, because you can't carry out the inverse in most cases without doing the partial fraction. Once you have your hands on this and you can deal with that, then you are good to go. Then we have a problem here, you know, to try your hand on. Quite simple. So we have that a system, you know, is given by this state space equation. So we can see that. Then what are we to find? We are to find what? The transition matrix using this. So find E of t. So of course we have gotten our transition matrix using that. This is our transition matrix. Then we have to also determine what? The zero state response if u is 10. Wow. So give it a try. Look for the zero state response if u is 10. Then you are also to look for what? The total system response. So what will be the total system response? Can you calculate the total system response? The total system response will be equal to the system response due to the initial conditions, or what we call the zero input response plus the zero state response. So you can individually get these two responses and add them together. So whichever one that you find convenient. Of course, you can also solve the entire circuit. Let me show you what I mean. Now, listen, look at this. So you can see this response here is the zero input response. This is the zero state response. So you can either solve this, then integrate by delaying this whatever you have here introduce tau, delay it by tau, then do your integration with respect to tau, u of tau. So that is to say, if you have u of t, you convert it, you deal with it as u of tau, then do the solution. Or you can just go in this form, then get this component, get this component. Of course, when you have this component and you have this component all in frequency domain, then you do what? The inverse Laplace transform to time domain, and that will give you your solution. So thank you so much for listening, and see you.